Hi, folks. This time we're going to talk about how to multiply and divide polynomials. So whenever you see a multiplication problem with parentheses, you should be thinking about the distributive property. And our first examples are just simple distributive property. Like in this example here, negative 2x times the quantity 3x plus 7. To use the distributive property, I have to take this term and multiply it by the first term, and this term and multiply it by the second term. I have to multiply what's outside the parentheses by what's inside each term inside the parentheses. So negative 2x times 3x plus negative 2x times 7 is an equivalent way to write this. I am going to do these problems pretty slowly in this example because we're still getting used to dealing with exponents on variables. So when I do negative 2x times 3x, that gives me negative 2 times 3 is negative 6, but x times x is x squared. And then when we take care of the second term, negative 2x times 7 is negative 14x. Of course, we can simplify this a little bit further. We don't need that extra negative sign, the positive and the negative sign between the terms here. So negative 6x minus 14x is our final answer. Let's look at another example, just distributing what we have outside parentheses with what we have inside parentheses. We have 3x squared times 5x squared plus 3x squared times negative 2x plus 3x squared times 6. Once again, 3 times 5 is 15, and x squared times x squared is x to the 4th. 3 times negative 2 is negative 6, and x squared times x is x cubed. 3 times 6 is 18, and we just have an x squared, so that stays as x squared. Once again, we can reduce that so we don't have a positive and a negative sign between terms. And we end up with the final polynomial 15x to the 4th minus 6x cubed plus 18x squared. So that's kind of simple, straightforward distributive property that you can use to multiply polynomials. Notice that whenever we multiply polynomials, we get a polynomial as our answer. How about dividing polynomials? What happens when you divide polynomials? If you only have kind of one component in the denominator, then we can just divide each term in the numerator by the denominator. So what that looks like is x to the 4th is going to be over x squared plus 4x cubed still over x squared plus 11x squared still over x squared. And if you think about it, when you add fractions, they have to have that same common denominator so that you can add them together. And this is the same thing that we're doing here in reverse. We're taking each portion of the polynomial in the numerator and putting it over that same denominator, giving it that common denominator. Well, now that I've written this as 3 separate fractions, I can see that these fractions can be reduced. If I have x to the 4th over x squared, when you have a division problem with powers where the base is the same, you can subtract those exponents and get x squared. Similarly here, if I've got 4x cubed divided by x squared, that x is the same base. I can do 3 minus 2, and 3 minus 2 is 1. So 4 times x to the first power, but I don't need to write that first power here. And when I have 11x squared divided by x squared, that x kind of x squared cancels out entirely. It divides away, and so we're just left with 11. So my final polynomial after dividing this way is x squared plus 4x plus 11. If we look at a slightly more complicated example, where we have a polynomial in the denominator, then we cannot use the same method that we did above. Not quite true. We can use the method that we do above, but never the way students want to. So for instance, I could write 6y over y minus 5 minus 30 over y minus 5. This is perfectly correct, and this is doing exactly what I did in step 1 above. I kept my common denominator and applied the common denominator to both terms. The problem is this doesn't help us. 6y divided by y minus 5, those have no components that cancel out with each other that I can divide away. So although you can write a correct statement, it's not actually helpful. So I'm going to scribble that out for now. And let's do something that's helpful. When you have a polynomial in the denominator, usually the best strategy to use to try to find the quotient, to try to simplify the fraction that you've got here, is to find a common factor in the numerator and the denominator. So y minus 5 is in the denominator. So can I find y minus 5 in the numerator? And the answer is yes, I can, because 6 and negative 30 have a greatest common factor of 6. And if I pull that 6 out front, I can rewrite 6y minus 30 as 6 times the quantity y minus 5. Of course, that's just the numerator. In the denominator, I still have y minus 5. And so I see here that once I have the same value in the numerator that I have in the denominator, then those terms divide away, and I'm left with just a value of 6. Now, it's important to note that what you cannot do, and students always want to do this, they always want to do, oh, this is really the same as 6y over y minus 30 over negative 5. Splitting, you can't just split the fraction like this. That is incorrect. Don't do it. This is incorrect. Don't do it. This was the correct way to kind of separate the components of the numerator by using a common denominator at the bottom. If you try to write the fractions this way, it's incorrect because those denominators, the denominators are not in common with each other. They're totally different denominators. So those values on top couldn't actually be added or subtracted from each other. One thing to note, and this becomes important later in algebra, the division is not defined when the denominator equals 0. So in part A, when I had x squared in the bottom, it is not, x can never be 0 in that problem. In part B here, when y minus 5 is in the denominator, y can never equal 5. Otherwise, the denominator would equal 0 and division is not possible. All right. We've seen some simple examples of how to multiply polynomials using the distributive property. But what happens when the polynomials get a bit bigger, when you've got a binomial or a trinomial? How do you use the distributive property then? And the key here is that you still distribute to each term in the polynomial, but this time I've got 2 terms. I have to take this first term and distribute it to each term in the other polynomial. And then I have to do the same thing with the 2. I have to distribute to the x, and I have to distribute to the 5. So if you look there, I've got 4 arrows where so there are 4 separate multiplication problems I have to think about. First, I have to think about the x times x. Then I have to think about the x times 5. Those were the ones I had written in green. What did I write in red? 2 times x. And then I have to think about the 2 times 5. So those are the 4 separate multiplication problems I have to think about. And if I do the multiplication, x times x is x squared. X times 5 is just 5x. 2 times x is 2x. And 2 times 5 is 10. So it looks like nice and clean now. It looks like a tetranomial, but you have to watch out because I have 2 like terms here that can be combined. So what I actually have is x squared plus 7x plus 10. So that's one way to think about the distributive property when you're multiplying 2 binomials together. Think about distributing each term of the first polynomial to each term of the second polynomial. Let's do another example. If I have x plus 3 times the quantity x minus 4, then I've got to think about distributing the x to both terms, and I have to think about distributing the 3 to both terms. So let's focus on those blue ones first. I have to do x times x. Then I have to do x times negative 4. And then in red, I need to think about 3 times x and 3 times negative 4. And what I get when I do the multiplication is x squared plus negative 4x plus 3x plus negative 12. I have like terms here in the middle, so I'm going to do x squared minus x minus 12 as my final answer. This isn't the only way to think about multiplying polynomials. We're going to use a table to kind of organize this multiplication of each term. Again, it's still the distributive property. We're going to get the same answer as we would for the previous examples. It's just another way to think about the multiplication. So if I look at this multiplication problem, the quantity 2x minus 3 times the quantity x plus 5, I'm going to take one of those polynomials and write them at the top of my grid as column headings. And I'm going to take the x plus 5 and write those as row headings along the side. Each term is its own column or row heading. And then I use this as a table to do multiplication. So 2x times x, well, that's going to be 2x squared. Negative 3 times x, that's going to be negative 3x. 2x times 5, that's going to be 10 with the x still there. And then negative 3 times 5 is negative 15. Notice we do have some like terms here that need to be combined. So our final answer is going to be 2x squared plus 7x minus 15. And that gives us our final answer. Always look out for those like terms so that you combine them. Now, when you're multiplying binomials, the methods that I've looked at so far work for any polynomial. FOIL, the next method we're going to learn, works only for multiplying binomials. But far and away, those are the polynomials we will multiply most in this class. The FOIL method is really just a way to organize the distributive method to make sure you don't accidentally skip any combinations or do any of them twice. FOIL stands for first terms, outer terms, inner terms, last terms. So if I do my first terms here in red, that's the first term times the first term. And then maybe outer terms here in green would be the outside term with the outside term. And then the inner terms would be the two that are closest together here in the middle, the negative 3 and the x. And then lastly, we have the last terms, which is the -3 and the -6. So really, this is the order that I was doing it above when I was doing the distributive property. But I've been doing this for years, so of course I'm used to just going in FOIL order. And for new students who are learning how to do this, it's easy to accidentally do the same one twice. If you're consistent about the order you're doing it in, you never accidentally miss a combination of to multiply, and you never do any of them twice. So let me color code this again as we do this example. My red terms, my first terms, that's going to be x times x. My green terms, my outer terms, that's going to be x times -6. My inner terms, my blue terms here are -3 times x. And lastly, my purple terms, -3 times -6. I can now add up the, or I'm sorry, actually do the multiplication problem. X times x is x squared. X times -6 is -6x. -3 times x is -3x. And -3 times -6 is +18. I do have like terms here I can combine. That's another nice thing about the FOIL method is that it will always put those like terms right next to each other. If they are like terms, it's possible to multiply polynomials that don't give you like terms. But typically they show up next to each other. And my final answer is x squared minus 9x plus 18. Let's do another example. And as always, I love it when you pause the video and try to answer the questions before I do. Try to find those first terms, outer terms, inner terms, and last terms, and practice multiplying those constants and variables together to get the right answer. I'm going to do 2x times 3x. And then my outer terms will be 2x times -5. My inner terms will be 1 times 3x. And my last terms will be 1 times -5. And when I do the math, 2 times 3 is 6, x times x is x squared. 2 times -5 is -10 with the variable x. 1 times 3 is 3. Keep the x there. And 1 times -5 is -5. Combining the like terms that exist, I end up with 6x squared minus 7x minus 5. Now, up to this point, all of the examples for multiplication have involved a binomial being multiplied by a binomial. It is possible to do larger problems like this binomial times a trinomial. And here, it's just the distributive property. Every term inside the first polynomial multiplied by every term in the second polynomial. So I'll have those 3 multiplication problems to think about, and then I'll have these 3 multiplication problems to think about. So let's write those down. I've got to think about x times x squared plus x times -3x plus x times -2. And then I'll switch to dealing with the 5 now. Plus 5x squared plus 5 times the -3x plus 5 times the -2. I jumped ahead of myself there. I should have kept that x squared separate. And eventually you won't need to show every single step along the way. But as we're first learning these, I think it's best to show all the steps. X times x squared is x cubed. X times negative 3x is negative 3x squared. X times negative 2 is negative 2x. 5x squared is just 5x squared. 5 times negative 3x is negative 15x. And 5 times negative 2 is negative 10. What like terms do we have here that we can combine? This is my only x cubed, but I've got an x squared here and an x squared here. I have a 2x, negative 2x here and a negative 15x here. And then I have a negative 10 all by itself. I want to write this in standard form, so I'm going to focus on that x cubed first. And then I'll do my negative 3x squared plus the 5x is positive 2x squared. Then I'll do my gray color here. Negative 2x minus 15x is negative 17x. And then I'll include my negative 10, which is my only constant here. So x cubed plus 2x squared minus 17x minus 10 is the final answer from multiplying these two larger polynomials together. So let's look at a real world example of when we might be multiplying polynomials together. Sometimes if you're looking for just the right ratio of measurements on something that you're building or something in sports, like for example, this trapezoid region on a hockey rink, we're going to write a polynomial that represents the area of this trapezoidal region here outlined in red. So the area of a trapezoid is 1/2 h times, let me just write this down, 1/2 h times b1 plus b2. So looking at this picture, I need to do 1/2. The height here is this vertical stretch, which is x minus 11. So my height is x minus 11. My b1 plus b2, my b1 is, doesn't matter which one's which. Let's call this one b1, this one b2. I've got x plus 6. All right, before we multiply these polynomials, let's simplify what we can, because we saw for question F that if I've got a 2-term polynomial times a 3-term polynomial, I have to do 6 separate multiplication problems. But when it was a 2-term times a 2-term, I only had 4 multiplication problems to think about. So let's simplify this second expression, the second polynomial, x minus 11 times 2x plus 6. That looks much more manageable. So I'm going to go ahead and focus on multiplying these together using the FOIL method. So I'll do the first terms first. I'll do x times 2x plus x times 6 plus negative 11 times 2x plus negative 11 times 6. Okay. And all of that should be in parentheses because I need to still multiply it by 1/2. I don't want to lose sight of this here. I've only combined these two polynomials. I haven't done anything with the 1/2 yet. All right. Let's make what I have in parentheses here a little less messy. I'm going to have 1/2 2x squared plus 6x minus 22x minus 66. And I can combine those like terms. So I get 1/2 of 2x squared plus, I'm sorry, not plus, minus instead. Minus 16x minus 66. And finally, now I can take that 1/2 and I can distribute it onto everything inside parentheses. So 1/2 times 2x is just, 2x squared is just x squared. 1/2 times negative 16x is negative 8x. And 1/2 times negative 66 is negative 33. So that is my final expression to represent the area of that hockey trapezoid. The second part of the question is saying, hey, if that shorter base B1 equals 22 feet, what is that area? Well, I should have written this as an equation. Area equals. We're just going to do area equals x squared minus 8x minus 33. I'm going to plug that number 22 in where I have that x. So 22 squared minus 8 times 22 minus 33. And if I plug that into my calculator, I get as my answer 275 square feet. So hopefully you have a bit more understanding now of how to multiply polynomials together. It does take some practice, but if you're systematic about it, step by step, you're less likely to get confused about which terms you've multiplied and which ones you haven't. I hope this helped.